this is going to be our second video in our capacitors and capacitance series. And in this video, we're going to be looking at different ways we can combine capacitors. So everything I'm going to be talking about here is from the textbook from section 24.2. And so let's get right into it here. We're going to be interested in combining capacitors. Capacitors come in a number of different capacitances and working voltages. We want to look at a few ways that we can combine these to get the capacitance we're actually looking for when we're trying to build, let's say, some sort of a circuit, right? So let's take a look at some of these different combinations we can build of these capacitors. And the two simplest sort of combinations we can build are a collection of capacitors in series or in parallel. So we'll take a look at both of those situations. And let's get right into it here with capacitors in series. Okay, so I kind of want to have this diagram on screen, but I want to keep the text on screen too. Okay, so in part A here of this diagram, we have two capacitors in series, right? So we have our potential difference between A and B, and then across some conductor we have our capacitor 1, and then in series connected to our capacitor 2. Okay, and so we're interested in sort of how the charge, how the capacitance, how the potential difference are all going to relate to each other in this system, right? So let's take a look at some of that. Okay, so the first thing that we can see is that we have this potential difference of VAB across A and B, right? And we can imagine that maybe we have a battery put in the system here that's going to give us that potential difference or something, right? And so as we connect this battery, it's going to charge our capacitor plates, and the first thing we want to realize is that the charge on each of these capacitor plates, or the charge for each capacitor, as we often talk about the charge for capacitors, is going to be equal. Okay, and we can see that right away, because we can see that as the top plate of a capacitor 1 here picks up a positive charge from presumably the positive terminal of our battery, it's going to pick up. So it's picked up this positive charge from A, and I guess it would depend how we set up the battery. But in the end, we can just say that this positive charge is coming from the battery, and so we have this positive charge, and now we have this induced negative charge in our bottom plate. But if we induce a negative charge in our bottom plate, well, this whole chunk here, this is just one chunk of conductor, so we need charge conservation here. We need no net charge to be present here, and so we're going to cause this buildup of positive charge on our bottom, or our top plate of our bottom capacitor here, right? So when we pick up this positive charge on the top plate of capacitor 2, this is going to induce a negative charge in the bottom plate, and we're going to end up with this situation here. But because of the configuration here, these are all going to have the same magnitude. We're going to have a plus Q here and a minus Q here, and because we have a minus Q here, we have a plus Q here, and because we have a plus Q here, we have a minus Q here, and this is connected back to our battery, right? So that's the first thing we want to notice here, that all these Qs need to be the same across both of our capacitors. Even if C1 and C2 are not the same, we need all these Qs to be the same. Okay. The next thing we kind of want to look at here is our potential difference, our potential drops across these points, right? So we know that our potential difference VAB is going to be put in here, right? But we want to see what our potential difference VAC and VCB are going to be. Okay, so let's take a look at that here, and we can kind of pull this out. What equation was that? I think it's equation 24.2 from the last set of videos, or from the last video, I should say. We can use that equation to kind of build these expressions for what our potential drops or our potential difference across points A, B, and C are going to be. So we can see here that our potential difference VAC, so that's our potential difference here, VAC, is going to be equal to Q over C1. Q is the same everywhere, like we just talked about. It has to be the same Q, and C1 is the capacitance of our first capacitor. Now, we often label this V1, and we're going to label VCB V2. And why do we do that? Well, because this is the first sort of capacitor in our setup, and this is the second capacitor in our setup, and that's just standard to sort of label them in that order. And then we call it VAB, just V, the total potential difference across A and B, right? And so we're going to see that they relate to each other in this way. VAC, which we now call V1, is equal to Q over C1, and then VCB, which we now call V2, is equal to Q over C2, okay? And our total potential difference, VAB, which we now call V, is going to be equal to V1 plus V2, and we can rewrite this using these expressions here as we see here. We can now rearrange this. We can now move this Q over, and we're going to pick up this as V over Q is equal to 1 over C1 plus 1 over C2, right? And as I mentioned, I have a little blurb here about how it's common to relabel these, okay? So what are we kind of interested in doing now? Well, we're kind of interested in thinking about how do we replace these two capacitors in series with a single capacitor that's going to do the same thing as these two did, but in just one capacitor, right? So we want to find what the equivalent capacitance we would need for this one capacitor would be to replace these two capacitors here, okay? And so that's the goal. So let's take a look at how we're going to do that. We want to find the equivalent capacitance, CEQ. And so CEQ can be defined as the capacitance of a single capacitor with which has this charge Q, which is going to be the same as the combination of all these other capacitors when the potential difference V is the same. So basically keeping V our VAB the same here, we need to find what this CEQ we need is to replace C1 and C2, right? That's the goal here. And it kind of sounds worse than it really is. In the end, it's a fairly simple relationship. We just take this relationship that we found above here. We're gonna remember that our C, and again this is just equation 24.2 from the last video. We're going to see that we can write C as Q over V. So our CEQ is just going to be Q over V for the whole system, right? We know that our Q is going to be the same across all the plates, and our V is going to be the total potential difference from A to B. If we take the reciprocal of this, well, this ends up being V over Q, but we just calculated what V over Q for this system would be. So we can substitute this in, and in the end it gives us this expression. And written in a slightly more general way for potentially more capacitors in series, we end up with this important equation here, which is telling us that for capacitors in series, we can write the equivalent capacitance as 1 over CEQ is equal to 1 over C plus 1 over C1 plus 1 over C2 plus 1 over C3. And basically what this is saying is that the reciprocal of the equivalent capacitance in a series of capacitors is equal to the sum of the reciprocals of the individual capacitors, right? Which is just this quote from the text, which I have down here, right? So this is really the takeaway message, this equation here, and we're going to do examples, so we'll see how it kind of all works out afterward. We also want to note that for these capacitors in series, our total potential difference, our VAB, which we now write as V sometimes, is actually going to be equal to V1 plus V2 plus V3, right? So the potential difference across AB is going to be the sum of the potential difference across AC and CB, okay? So that's basically capacitors in series. Let's now take a look at capacitors in parallel. And so in parallel, well, I'll show us the diagram here. So we see the diagram here. This is basically two capacitors set up in parallel. And again, we're going to ask the question, how could we replace these two capacitors hooked up in parallel with a single capacitor that's going to give us the same characteristics of that system with two capacitors, right? And so this diagram that we have here, this is diagram 24.9a from the text. And let's note here, maybe the first thing to note is that our potential difference, our VAB across A and B, is now going to be the same across AB as it is across capacitor 1 as it is across capacitor 2, right? And the way to see that is that this whole top chunk, both of these positive plates and A, are all one conductor, right? They're all sitting on basically one potential because they're all connected. They're all one chunk of conducting material. And the bottom plates, along with B, are all connected through one conductor as well. And so all the stuff on top has to be at the same potential, and all the stuff on the bottom has to be at a different potential. And so across, however we jump across, we're going to be going across this potential difference, VAB. Okay, so in this case we have VAB, which we call V, is equal to V1 is equal to V2 is equal to V3. And this is different from the situation we had above in series, where V was equal to V1 plus V2 plus V3, right? So that's important to keep in mind, the difference between capacitors in series and in parallel, okay? And so now we want to take a look at the charges on these capacitors and how they relate to the charge on our equivalent capacitor. But first we just take a look at the charges on each of these capacitors. Unlike the case of the capacitors in series, these capacitors don't need to have the same charge on them. Q1 doesn't have to be the same as Q2 here. They can be different, and we can see how they relate to C1 and C2 here, right? So for Q1 needs to be equal to C1 times our potential difference, which is just V here because V is the same everywhere, right? And Q2 has to be equal to C2 times V, okay? So that's how our charge relates to our capacitance and our potential difference for these setups. Okay, so now we want to find what the Q, well, basically we're trying to get at what the configuration of this single capacitor is going to replace these two capacitors in parallel is going to be. First, we look at the charge that we're going to need to have on this single replacement capacitor, and we can see that the charge that we're going to need to be Q1 plus Q2. We need all the charge that was on C1 and well all the charge that was on capacitor 1 and all the charge that was on capacitor 2 to be accounted for in our equivalent capacitor over here. So we need Q equal to Q1 plus Q2, and we can just use the expressions that we had above here to rewrite Q1 and Q2 in these terms. And if we shuffle things around, we can see it ends up looking like this. Okay. So again, using equation 24.2 from the last video, we can see that this combination is just equal to our CEQ here, and this leads us to our second important relationship between capacitances, but this time it's for capacitors in parallel. Okay, so the equivalent capacitance of our single capacitor is going to replace however many capacitors in parallel is going to be that we're going to need our equivalent capacitance to be equal to C1 plus C2 plus C3. So no longer the reciprocals, which is what we needed for capacitors in series, but now it's just the sum of all the different capacitances. And again, this is telling us that the equivalent capacitance of a parallel combination of capacitors is the sum of the individual capacitances, like this quote from the text here. Okay, and in this case, unlike the situation for capacitors in series, our Q's are all different, and our total Q, our Q is going to be equal to Q1 plus Q2 plus Q3. So the charge on our equivalent capacitor needs to be equal to the sum of all of the charges on all of the capacitors that made up the system before, right? So a lot of this stuff sounds a little bit worse when we're sort of just talking about it, but the actual calculations for stuff like this ends up being not too bad at all, as long as we do it in a sort of systematic way. So let's do some examples here. This first example is 24.5 from the text. We're looking at capacitors in series and in parallel. And so we're basically going to be looking at both of the diagrams we had above. We're now going to be setting C1 and C2 to some value, and we're going to actually calculate some stuff about the equivalent the equivalent capacitor. We're going to be looking at the capacitance of that equivalent capacitor. We're going to be looking at the charge and the potential difference for some of these situations. Okay, so we're going to start off by looking at the capacitors in series. I wish I had put the diagrams here maybe in smaller form, and I'm not going to try and scroll up and down too much here. So if you need to, just pause the video and remind yourself of what the first diagram looks like. But the first diagram is just two capacitors in series, and we want to find what the equivalent capacitance of a single capacitor would be to replace those two capacitors in series. So the way we're going to do that is equation 24.5 from above is going to give us this expression. It's basically just the one where we saw the reciprocal of the capacitances, and it's just basically going to tell us that our CEQ is going to be equal, well, our 1 over CEQ is going to be equal to 1 over C1, plus 1 over C2, and so this is going to lead us to an expression like this. We're going to have 1 over 6, and these are all in microfarads, but I won't put in the units, and we're going to be 1 over 3 for the second one. This is going to be equal to 1 over 6 plus 2 over 6, which is going to be equal to 3 over 6, which is equal to 1 over 2. And this tells us that CEQ is equal to 2 microfarads. Okay, and so if we had those two capacitors from above connected in series, and one was 6 microfarads and the other one was 3 microfarads, and we replaced both of them with a single capacitor, it would need to have a capacitance of 2 microfarads. Okay, so that would be the first answer to let's say part A, or wherever we're looking at the series setup, right? Now, if we're interested in the charge on this single capacitor that we're replacing these two capacitors in series with, well, we can simply go to equation 3 from above, where we have CEQ is equal to Q over V. We can just rearrange this a little bit to get Q equals CEQ V, and then we just substitute in numbers. If we want Q on our new equivalent capacitor, well, that's just going to be 2 microfarads times 18 volts, which is our potential difference. If you do that calculation and clean up your units, you're going to end up finding that this is 36 microcoulombs. Okay, and so that would be our Q on that single capacitor that we've now replaced both capacitors with. It needs this charge here. Okay, and now we want to see what. Now let's think about what the potential difference across AC and CB are. So maybe it's worth scrolling up for this one. So we're now going to calculate, given these new values that we've been given, the value of C1 and the value of C2, we want to see what the potential difference AC is and the potential difference CB is. Okay, so we're going to look at those two potential differences, and we know that should add up to our potential difference VAB, which we now call V when we're talking about these circuits. Okay, and I really hope this doesn't crash, because I had a crash before, but let's see how this goes. Okay, so to find this, we're simply going to use equation 1. This is going to tell us that V1 is equal to Q over C1. And so we can just substitute in numbers. This is going to end up giving us well we know what Q is, right? Because we just calculated what Q is, and Q has to be the same. Q has to be the same in both situations, because we have the same charge in both capacitors, and we have that same charge in the single capacitor that we're replacing both old capacitors with. And so this is just going to be 36. This will be microcoulombs. And we're going to be over, it's going to be 6 microfarads here, and so we're going to end up with with a 6 volt potential difference there. And in the case of V2, which is really just VCB, right? Maybe I can. So V2 is going to end up being just Q over C2, and this is again just going to be 36 over 3 now. It'll be microcoulombs over microfarads, and this is going to end up giving us 12 volts. Okay, and so this is great because now we can sort of verify that if we add these up, we know that V1 plus V2 has to equal our V. We can see that this is 6 plus 12. This is equal to 18, and 18 is exactly the potential difference that we're given here for VAB. So the whole thing checks out, and we now have sort of numeric values for a number of the quantities that we're looking at. Let's take a look at a second example here, which is basically, okay, so we start off with this setup here. We have what do we have? 1, 2, 3, 4, 5 capacitors set up in this sort of collection of series and parallel, all kind of connected up. And we want to replace this whole thing with a single capacitor that's going to give us the same capacitance. Okay, and so let's sort of take a look at how we go from diagram A to diagram B to diagram C and finally to diagram D. We can see what the final answer is going to be here, but let's sort of follow the steps on the way through, right? Okay, so let's start off with or actually before I do anything, let me save this and we'll start it up in a second. Hold on. Okay, so let's get to this next one, but before I do get to this next one, I just realized that as I was paused and saving my PDF here, that I had forgotten to do the parallel portion of our first question here. So let's quickly jump back. I'm just going to make like a slash here, and we'll quickly do the calculations for our parallel setup. Okay, so in the parallel setup, we want to again find what our CEQ needs to be to replace these two capacitors in parallel, and we're going to want to see what our potential difference is and what the charge on these different setups are going to be, right? So let's take a look at that really quickly. So the first thing we know is that that for this setup, well, we're always going to have a VAB, which we call a V of 18 volts, right? And this is because, like we talked about, the potential difference between A and B is going to be the same as the potential difference across these, which is going to be the same as the potential difference across our equivalent capacitor, right? Because it's all, this is one chunk of conductor, this is one chunk of conductor, this is a different chunk of conductor, just as this is a different chunk of conductor. Okay, so the potential question is kind of easy here. The equivalent capacitance is also easy. Equation 24.7 here makes it very easy for us. So CEQ is just going to be equal to C1 plus C2, which is just going to be equal to what were those values? Is it 6 microfarads and 3? So that's just going to give us CEQ equal to 9 microfarads. Okay, and then we want to know what the charge is going to end up being, right? And so let's find the charge first on each of our capacitors here. So we're going to do the first one and then the second one, and then we're going to know that Q needs to be Q1 plus Q2. Okay, and so given the values that we have here, we can see that from equation 6, we can see that Q1 equals C1V and Q2 equals C2V. And so very quickly we can just substitute in those values. C1 again is 6 microfarads, and we have an 18 volt potential difference here. And again, we're going to have the same 18 volts in the second case because we have the same potential difference across both of these capacitors. If we do this calculation, we have to be careful here because I haven't included the microfarads, but it's going to be 6 microfarads times 18 volts. This is going to end up giving us 108 microcoulombs, and in this case we have 54 microcoulombs. Okay, and we know that Q needs to be equal to Q1 plus Q2, and this is going to end up giving us what does that give us? 162 microcoulombs. Okay, so that's the charge that we would need on these plates here. Okay. Okay, so now let's actually move on to example 24.6, and what we're looking at here is combining this sort of set of 5 different capacitors, which are all hooked up in a different way. We want to break it down to a single capacitor that's going to give us the equivalent sort of capacitance of all of these capacitors separately, right? So let's go through and kind of see how we jump from diagram A to diagram B to C and then finally to D. Okay, so in the jump from A to B, this is how we go from diagram A to B. What are we doing? Well, we're trying to collapse down this set of 2, and this is kind of how you would do it if you were just given this problem, right? Like, let's say you didn't have all these steps. You would say, well, what's the smallest thing that I can collapse down, and then what's the next smallest thing? So the smallest collection here that you can easily collapse down is these two capacitors in series, and so we want to start off by using 1 over CEQ is equal to, well, the reciprocals of these values, right? So it's going to be 1 over 12, and so all values in microfarads. So I don't have to bother writing that down. So we're always carrying around this 10 to the minus 6 farads factor, okay? And so we're going to need this equation here. So our equivalent capacitance, or the reciprocal of our equivalent capacitance, is going to be equal to the reciprocal of these two capacitances here. If we solve this, we're going to end up with, what do we end up with? 3 over 12, which is 1/4, which means that we end up with a CEQ equal to 4, and that's exactly what we find here. That's this step over here. Now, when we're at this step, we have 3 capacitors hooked up in parallel, and we want to go from these 3 capacitors to a single capacitor over here. We're hoping we find the result 18 microfarads. Let's see if that ends up being the case. B to C. Well, B to C is very easy because we're dealing with capacitors in parallel, and so we use the other equation. This is just going to be 3 plus 11 plus 4, 15, 18. Okay, so that's 18 microfarads again, and we do find the result that the text has for us here. Finally, we want to go from this setup of two capacitors in series again, and so C to D is going to end up giving us a result where we need to find 1 over CEQ is equal to 1 over 18 plus 1 over 9. This is going to end up giving us 3 over 18, which is going to give us 1 over 6, which means that CEQ is equal to 6, and I'll put in the final microfarads here. Okay, and so that's the value that we find here, and so we can see how we can build these complicated collections of capacitors in series and parallel, any combination we want, and we can kind of, by using, let's say we only have these fixed values, right, and we wanted to get to this value. Well, in this case it would be kind of dumb because we have this 6 microfarad capacitor here, but let's say we needed not just capacitance but other characteristics of the capacitor. We could sort of build the whole thing up, and we can see how we can calculate what the effective sort of capacitance or different characteristics of that capacitor would be by using these relationships to sort of add them up and see what the resulting single capacitor replacement would look like. Okay, so that's capacitors in series and in parallel, and we're going to have, I believe, one more video in this series, so it's only going to be 3 videos for this chapter because we're not doing anything to dealing with dielectrics, but I'll talk about that more in the next one, and I'll see you guys in the next one.